Hello students, today I am going to discuss another important theory from the first chapter of the class 12, that is Gauss Law and its applications. Okay, so before going to the Gauss Law, we need to know the electric flux. Okay, electric flux. What is electric flux? আমি সবাই জানো electric flux মানে কি? So electric flux is nothing but the number of field lines passing through a particular area. Okay, so this is mathematically defined as the E dot product of electric field vector and the area vector, where E is the electric field vector and this is the area vector. Okay, so this is simply your electric flux and this is defined by this phi. Okay, this is the surface integral. Okay, so this is for the open surface. This is for the open surface. So for closed surface, it is written as, using this symbol, we can write it for the closed surface E dot, this is the dot product basically, electric field vector and the area vector is equal to phi. So this is because of the closed surface. Okay, this is written for the closed surface. Okay, so we all know that area is a vector quantity. Area is a vector. For open surface, the direction of the area vector is away from the surface. Okay, for closed surface it is also normal to the surface and away from the surface. Now for Gauss law, what Gauss law says, Gauss's law, the total electric flux or the net electric flux through a closed surface, okay, through a closed surface is q in by epsilon naught, where q in is the charge enclosed by the Gaussian surface, enclosed by the Gaussian surface, and epsilon naught is the permittivity of the free space. Okay, permittivity of the free space. Okay, so mathematically it can be written as integration, this is the symbol for the closed integration over the closed surface, that is E dot ds is equal to q in by epsilon naught. Okay, so Gauss law মতে কি হয়, electric flux through a closed surface সদায় q in by epsilon naught হয়, and where this q in is the charge enclosed by the Gaussian surface and epsilon naught is the permittivity of the free space, and mathematically this is defined as like this, E dot ds is equal to q in by epsilon naught. Moreover, আৰু যদি মই কওঁ ইয়াক আমি অকমান যদি ভাঙি কেনে লিখো তেতিয়া কি হ'ব, আমি ক'ব পাৰো, what does this mean? Suppose I have a closed surface like this. Okay, I have a closed surface like this, and here is a charge q1, here is a charge q2 and q3, and there is another charge q5 out of this and q4 out of this closed surface. Okay, now this surface, closed surface through which we are finding out the electric flux is called the Gaussian surface. Okay, sometimes it is called the Gaussian surface. And another important point is this Gaussian surface cannot pass through the surge, Okay, now for this system we can write the electric field E dot ds field electric flux. Okay, integration. So we can write it as E dot ds for a whole surface. This surface. This is the closed surface. This is not the line. This is not the line. Okay, line boundary. It is only the surface boundary. This is the closed surface. Okay. So E dot ds, it can be written as Q in. What are Q in? Q1 plus Q2 plus Q3 divided by epsilon naught. But electric field in the left hand side, this electric field is because of all the surges. E due to Q1 dot ds, okay, plus E due to Q2 dot ds plus E due to Q3 dot ds plus integration E due to Q4 dot ds plus integration electric field due to Q5 dot ds is equal to Q1 plus Q2 plus Q3 by epsilon naught. Means, according to the Gauss law, the electric field what we will calculate, this electric field is due to all the surges present inside and outside the Gaussian surface. Okay, so we can write this electric field that we are calculating, okay, is due to all the surges. This is the important point. Okay, all the surges present inside and outside the Gaussian surface, outside the Gaussian surface. But the surge in the right hand side, okay, of this Gauss law, I mean this one Q in, that is Q in is only the surges inside the Gaussian surface, only the surges inside the Gaussian surface. Okay, so now this is all about the Gauss law. Okay, so these are very important points. Now another important point is Gauss law is valid for all the system. Gauss law is valid for all the surge system, but it is easier to calculate for highly symmetric surge system. Highly symmetric surge system. Okay, highly symmetric surge system. So these are two very important points regarding the Gauss law. Okay, now let me write the Gauss law again. This is our Gauss law, integration E dot ds, and this is for the closed surface. Okay, so Q in by epsilon naught, where E electric field, this is the electric field due to all the surges present inside and outside the Gaussian surface. But in the right hand side, these surges Q in, here we need to take into account only those surges which are inside the Gaussian surface. Okay, now using this Gauss law, we can find out or we can calculate electric field because of the highly symmetric surge system. Okay, so for this we have three important applications that we will be dealing with. That is, one is electric field. First is electric field. Electric field due to an infinitely long surged wire, infinitely long surged wire of surge density lambda. Okay, surge density lambda. So this will be our first application of the Gauss law. Okay, this is our first application of the Gauss law. So for this, let me consider. So for this, let me consider one. Let us consider one infinitely long surged wire, infinitely long surged wire of surge density lambda. Okay, surge density lambda. So let me draw this infinitely long surged wire. Okay, so let me draw this. I will draw this here like this. Okay, so this is your infinitely long surged wire. Here it extends up to infinity. Okay, so here is also it extends up to infinity. So it is infinity. Here is also it is minus infinity. So infinity to infinity. This is infinitely long surged wire of surge density lambda. Okay, now this is a very highly symmetric case. So for this, what we will do, we will draw one. Let me take one cylindrical Gaussian surface. Let a point P at a distance r from the wire where we need to calculate the electric field. Okay, electric field. Okay, so here we will draw one cylindrical Gaussian surface like this. Okay, one cylindrical Gaussian surface like this. This is your point P at which we need to calculate the electric field, which is the distance r from the wire. This wire is having a surge density lambda, but from the symmetry, from the symmetry the electric field at a distance r is normal to the wire, normal to the wire, and its direction is radially outward. Outward for each and every point on the Gaussian surface, on the Gaussian surface. Okay, on the Gaussian surface. So if we draw the electric field, you see this is the electric field direction at point P. Here also it is in this direction. So these are the electric field and they are equal. Okay, and they are always readily outward, okay, from the wire. That means if we use the Gauss law now, okay, we need to find out integration E dot ds equal to q in by epsilon naught. Okay, now what is E dot ds? It has three surfaces, you see. It has three surfaces. These are, this is one curved surface, number two circular surface, and number three is also circular surface. So for electric flux, so we can write electric flux through curved surface, curved cylindrical surface, plus flux through circular surface, two circular surface. Okay, this is equal to q in by epsilon naught. Now q in is how much? So this wire is infinitely long. Let the length of this cylinder be L. Then this much of the surge, okay, if it is positively charged, having positive charge density lambda, then this much of the charge is enclosed by the Gaussian surface, cylindrical Gaussian surface. So what we can write, the charge enclosed by the Gaussian surface, we can write it as, since lambda is the charge density, that means lambda is equal to charge per unit length, okay, per unit length. So that's why the charge enclosed by this Gaussian surface only in this much of length, that is equal to q in can be written as lambda into L. Okay, so putting it in the Gauss law, what we have, okay, what we have is, you know, this electric flux through the curved surface is what? E dot ds. Since electric field is E on every point of the cylindrical surface, because it is equal, E dot ds, and if we look for any area element, on the Gaussian surface, you see, for any area element, the area vector is parallel to the electric field for each and every point of the curved surface. Okay, but for the two circular surface, this is the area vector direction, okay, ds, and this is the area vector direction, ds. But at this point, electric field is perpendicular to the area vector for two circular surface. Okay, so E dot ds for cylindrical curved surface, okay, cylindrical surface, for cylindrical surface, this will be equal to what? E dot ds, since electric field direction and the area vector direction for each and every point on the cylindrical surface is parallel, so we can write it as E ds. Okay, and if we integrate this, electric field is having the same magnitude over all the cylindrical surface, so E into ds. Now we will have it as E into, what is ds for cylindrical surface? It is 2 pi rl, integrating all the surface, okay, 2 pi rl, since radius is r and L is the length of the cylinder. Okay, so for these two surface, electric flux, this two surface, this will be 0, because E dot ds, electric field vector and area vector are perpendicular, so there will be cos theta term, cos 90 degree, that will be 0, so flux will be 0 through this. Okay, so what we are left with is E into 2 pi rl. Okay, and this must be equal to q in by epsilon naught. So q in by epsilon naught, q in is your lambda L, So putting this lambda L by epsilon naught, we are left with E equal to how much? This L will got cancelled with this. So E will be equal to lambda by 2 pi epsilon naught R. So this will be the electric field due to the infinitely long surged wire at the distance r from the wire. Okay, now one more modification. If we want to do this, then we can easily do it. If we multiply 2 here, 2 lambda, then here 2 into 2 4. Okay, 4 pi epsilon naught r. So we will be left with 4 by 1 by 4 pi epsilon naught. You can write it as k. So 2k lambda by r. So this is the electric field, and direction is always radially outward from the wire if the surge density is positive, and if the surge density is negative. If the surge density is positive, okay, then electric field is away from the wire, and if the surge density is negative, okay, lambda and minus lambda, then the electric field will be towards the wire but normal to the wire in both the cases. Okay, so this is our first application of the Gauss law. Okay, I hope all of you have understood this problem. Okay, next application is so if we have this equation equal to lambda by 2 pi r epsilon naught, then we can have the graphical representation for this electric field versus r. Okay, you can draw this very easily. So graphical representation is very important. Let me draw this. Okay, if this is your okay, this is the coordinate system. Here we are having the variation of electric field with distance r. Okay, here it is electric field, so it will be like this. Okay, it will be like this. It is because it is E is proportional to 1 by r. Okay, so that's why. So next application is electric field due to an infinitely long charged sheet. Due to an infinitely long charged sheet or surface. Charge the surface. So for this, let us consider a surface, infinite surface of charge density sigma. So charge density sigma. Sigma means charge per unit area. So we will draw a surface here. Okay, we will draw a surface here. This is your infinitely long surface charge. Okay, this is your surface, and this surface is like this, infinity towards this, infinity towards this. It will go like this, to minus infinity go to plus infinity. Okay, so let me consider one point, which is point P, where we need to find out the electric field. This is the field point. Okay, this is the field point. Just field point. So the Gaussian surface here will be the Gaussian surface here is a small cylindrical Gaussian surface. Okay, or you can say small pillbox. Okay, pillbox also like this, containing this surface. Okay, this one, small pillbox. So it will be like this. This is containing this one. Okay, so from this, here is we have three surfaces. One is cylindrical surface, two circular surface. But for now, this is this. If this is the positive charge density, it is having the positive charge density. Then it will have the electric field here along this direction E. Okay. From the symmetry, the electric field will be along this direction only. Okay, along this direction only. So for the cylindrical Gaussian surface, you see the for each and every element on the cylindrical surface, area element or area direction is perpendicular to the electric field. Okay, so for this, electric flux will be equal to 0 because they are perpendicular to each other. If you write E dot ds, E dot ds for the cylindrical Gaussian surface, then you will get 0. Okay, now for this one, suppose this area is A and this area is B. Okay, the area of cross section will be same, AA. If AA, then E dot ds is equal to Q in by epsilon naught. Now here there are two surfaces, flux due to all the surface, first one is flux through this cylindrical surface, and that will be equal to 0 because area vector is perpendicular to the electric field vector, and electric field vector is radially outward because of the symmetry, as you can see. Okay, now for other two surfaces, electric flux, we can write it as E dot ds plus E dot ds. Okay, E dot ds. You see, they are parallel to the electric field here is in this direction, electric field is in this direction, area vector is along this direction, they are parallel. So we can write EA plus EA because area of cross section is A, and the charge containing this. Okay, this is the area. This is the area of the Gaussian surface. This is the area which is enclosed by the Gaussian surface. Okay, this area, and this area is equal to this area, and this area is, we have taken it as A. Okay, so what will be the Q inside? Q in is equal to nothing but sigma into A. Okay, sigma into A. So Q in by epsilon naught, we can write it as sigma into A by epsilon naught. Okay, this will be equal to 2 into EA is equal to sigma A by epsilon naught. This AA will got cancelled. Then we'll be left with E equal to sigma by 2 epsilon naught. Okay, and this is the magnitude of the electric field at a point which is very close to this infinite long surface surge sheet. Okay, and it is always radially outward and inward. Radially outward for positive charge density, and radially inward means towards the, and perpendicular to surface towards the surface for negative surface charge density. Okay, this is the second application of the Gauss law. Then our third application is electric field due to a thin spherical shell of charge density sigma. charge density sigma. Okay, charge density sigma. So let me draw one thin spherical cell. Okay, so let me draw this one as the thin spherical cell. Here we have the surges like this. All surges are distributed over this. Okay, so let sigma be the surface surge density. This is the surface surge density, that is surge per unit area surge density, and we need to find out the electric field inside and outside the spherical shell. Now first one is for inside point. Now for derivation যেটা পরীক্ষা করি, when we will do this derivation in exam, we need to write it here. Let us consider a spherical shell of radius small r or capital R, like this, capital R of radius capital R. Though for any inside point at a distance r, from the center, but here r is less than capital R. It shows we are finding out or calculating the electric field for point inside the spherical shell. Okay, so for this, let me take one point. This point P, where we need to find out the electric field. So we'll draw a spherical Gaussian surface passing through the point P, where we need to find out the electric field. Okay, it will pass through the point P itself. Okay, so if we write the Gauss law, E dot ds, it is very simple. E dot ds over this Gaussian surface, it should be q in by epsilon naught, right? But in the left hand side we have E into, if electric field is E, then ds is your, this is your r, right? R. So 2 pi r. No, it is not 2 pi, it is 4 pi r square, because it is a spherical surface. So 4 pi r square. So q in is 0. Now there is no surge enclosed by this Gaussian surface. Okay, so surge enclosed is 0 by epsilon naught. So this implies E equal to 0. Okay, since surge enclosed is 0, so that's why electric field inside the spherical shell is 0. Okay, now for any point outside, case B, for any point outside the spherical shell, that is for r greater than r. Okay, distance which is greater than r. So if we do this for any outside point, you see, we'll do it here. Okay, let me take another Gaussian surface for this. Okay, which will be at the outside of this spherical shell. Now, but in the exam you need to draw the two separate diagrams. Okay, two separate diagrams. I have shown it here for in only one diagram. Now this is the r and the point P is here. Now the point P is here. Okay, this is the point where you need to find out the electric field. So for this, what we will do is your integration E dot ds. If E is the electric field, at the point P over this, then Q in by epsilon naught. Now you see this Gaussian surface, which is outside this spherical shell, this is enclosing the whole surface charge. Okay. Now surface charge density is sigma. So Q inside will be equal to sigma into 4 pi capital R square, right? Capital R square divided by epsilon naught. Now E is symmetrically on all the, if the Gaussian surface is spherical, so you see from the symmetry, the electric field is symmetric or having the same magnitude on each and every point of the Gaussian surface. So E dot ds is your 4 pi R square, right? So if we do this, electric field will be equal to like this, sigma into 4 pi R square divided by 4 pi R square by R square epsilon naught. Okay. Now if we proceed with this, this will give you what? This will give you the sigma into 4 pi R square is the total charge, Q total on the surface of the spherical shell. This is E outside, 4 pi epsilon naught R square. Now this 4 pi epsilon naught is K, so we can have KQ by R square, where Q is the net charge or total charge on the surface of the sphere. Okay. So conclusion is, for any point outside, okay, for spherical shell, for R less than capital R, electric field equal to 0, and for R greater than R, the electric field equal to KQ by R square. Okay, this is KQ by R square. So graphical variation is, graphically we can show this as the variation of electric field with the distance R, which is the distance from the center of the spherical shell. This is R, and this will be here, it will be electric field. So this point, if this point is R equal to R, up to this point the electric field is 0, right? And from this it will again vary with R as 1 by R square. So this will be the graphical variation, okay, for any spherical shell. Okay. Now next application is, for the solid sphere of uniform charge density. Okay, electric field due to a solid sphere of uniform charge density solid non-conducting sphere. Okay, non-conducting sphere of uniform charge density rho. Now the charge is distributed over the volume of the sphere. Okay, volume of the sphere. This is the fourth application. This means rho is the volume charge density here. Volume charge density. Okay. Let me draw this. Okay. Let us consider one solid non-conducting sphere of radius r having charge density rho. Now we need to find out the electric field. Electric field inside. Okay, for electric field inside, that is r less than r, we will consider a Gaussian surface. This is the point P. We will consider a spherical Gaussian surface like this. Okay. At the distance r, so up to this, the Gaussian surface, from the symmetry, the electric field will be E dot ds integration, okay, E dot ds will be equal to q in by epsilon naught. So this is very simple. Since charge is distributed over the volume, so we can write here as electric field is E and ds is your 4 pi r square. Okay, so q in is your now q in will be equal to sigma into 4 by 3 pi r cube, because the charge will be enclosed within this Gaussian surface, by epsilon. So electric field will be given by sigma into 4 by 3 pi r cube divided by 4 pi r square, epsilon naught. Okay, so r square will got cancelled and that will be r, and now this will be sigma by this 4 pi will got cancelled, sigma by 3 epsilon naught into r. Okay, so this is the electric field inside at any inside point at a distance r from the center of the spherical sphere. Now for any outside point, again, if we do it for any outside point, let me take this as the outside point P, and if we want to calculate the electric field any outside point, for any outside point, suppose this is your Gaussian surface. Here the Gaussian surface we have considered, this is the point P where we need to find out the electric field, this is the R. For outside point, that is R greater than R, again E dot ds is equal to q in by epsilon naught. Again we will use the Gauss law. Okay, so electric field here is symmetric, so E into ds is your 4 pi r square, but now q in is the whole source. Okay, that is rho, it is not sigma, you can take it rho, this is taken rho. Okay, this is the rho. Okay, so rho r by 3 epsilon naught. So rho into 4 by 3 pi r cube, okay, r cube divided by 4 pi r square epsilon naught. Okay, this is epsilon naught. One more equation, more steps, to rho into 4 by 3 pi capital R cube. If we see very closely, then we can have this one as this is the total charge. Okay, this is the total charge q on this sphere or in the sphere. So q by 4 pi epsilon naught r square. Again 1 by 4 pi epsilon is k, so kq by r square. Okay, so this is the electric field due to this for any inside and outside point for a solid non-conducting sphere having charge density rho. Okay, so for the graphical variations, if you want to have the graphical variations for this, okay, we can have this. Okay, so for this we can write it as, for r less than r, that means inside point, it is rho r, electric field you can write as rho r by 3 epsilon naught. That means E is proportional to r, and for r greater than r, it is equal to kq by r square, that is E is proportional to 1 by r square. So if you vary this, okay, if you have the okay, if you have the graphical variation of this, then you can have this one. Here this r is electric field, so somewhere here it is r equal to r, so up to r equal to r, you see there is variation, linear variation, then it will be this one. This is the graphical variation of this electric field because of the solid non-conducting sphere having charge density rho. So I hope you have, all of you have understood this these applications of the Gauss law and what is Gauss law. So it is very very important from the point of view of board examinations as well as the entrance point of view. So if you have any doubts and if you need any such topics that I need to explain to you, please feel free to ask me. Thank you.